All right, today we're working on this beast. We ought to call it server 4014 because, you know, we're doing a big AI training on it, or at least, well, Union Pacific will get that one. This monster is the Gigabyte R284A91 chassis we looked at before. It's still packing two 128 core Intel Xeon 6980p CPUs. That's right, 256 cores total in here, 512 threads. What's special beyond that is that it supports insanely fast DDR5 8800 memory, and it has up to 20 front E3 slots, 16 of those supporting CXL memory expansion modules. Like these from Smart Modular. We've got a great platform for demoing lots of workloads, big CPUs, big memory, and big expansion. We've been doing videos on DeepSeek quantization and getting it, you quantize on this platform so you can run on a gaming computer. And the work we've done is giving the big names in AI quantization a run for their money, which is vicariously exciting. But here's the thing, it's not just AI workloads that benefit from CXL. In this video, we're going to break down the new CXL option for administrators, how you can use it in your servers, in other words, how it works, real world problems that it can solve, that sort of thing. CXL is almost mainstream here in 2025, and system administrators need to understand where it can help them solve problems. At least I think that, because I've been having a lot of fun discovering things. Stick around, you might be surprised where CXL can fit in and solve problems. All right, let's take a closer look at what we're working with here. First up, this chassis is the Gigabyte R284A91, the AAL3 configuration. It's actually pretty unique. You've got these 20 E3 slots right up front. They're hot swappable, well, not in CXL mode, but E3 is a form factor you might not be familiar with for storage. Most of them are wide, or 2T, to accommodate things other than storage though. In our case, CXL, but FPGA or even an ASIC accelerator would fit and work just fine here. It's PCIe lanes. CXL, at least for these 16 marked slots, supports CXL Type 3 memory expansion modules. That's what we've got here. But it's worth noting that CXL modules don't have to be in an E3 format. They can also look like a PCIe card, and we've done some videos on that in CXL and Smart Modular in the past, so check out those videos. CXL format is really convenient versus PCIe in this type of chassis though, because you can just add it to the front. It's also important to understand that CXL, it's not really PCIe. You can't just buy a CXL module if your server has a PCIe slot or an E3 bay. You have to have platform support for it. That means motherboard and BIOS support. Our CXL modules from Smart Modular that I've been testing are of the 64 gigabyte and 128 gigabyte variety. So if we add 4 of those expansion modules here at the front, we're adding another 256 gigabytes of memory in the case of the 64 gig modules. The rest of the system is the best Intel server you can get right now. It has dual Intel 6980p CPUs. It's 128 cores each for a total of 256 cores in this chassis, or 512 threads. Each one has 12 memory channels per socket, running it up to DDR5 8800 mega transfers per second. Right now, we've got it populated with 1.5 terabytes of DRAM. This is pretty much what you want if you're running monster AI workloads, giant in-memory databases, or pretty much anything that needs big compute paired with big memory, at least as far as memory bandwidth or memory expansion goes. When you think about adding CXL devices here, think of it like giving yourself a little bit more breathing room. You're not ripping out DIMMs to add more memory, so there's cost savings there, because it would cost me a lot of money if I went to 3 terabytes. You're just adding modules to expand capacity. You're keeping your main DRAM bandwidth fully utilized, but you're adding a little something extra. These modules will max out the PCIe Gen 5 bandwidth, and each module supports up to 8 lanes of PCIe Gen 5 bandwidth. And this is the system we've been using for our DeepSeek quantization demos. And honestly, the results we've been getting give the big names in AI quantization a run for their money. But today's video isn't just about AI. We're going to explore other workloads where CXL makes sense, because that's what I've been working on for the last few months. And more importantly, where CXL doesn't make sense. It's a bit loud in here, so let's go back to my desk and discuss further. So let's take a moment to break down what CXL actually is and what it isn't. CXL stands for Compute Express Link. There are different types of CXL devices, but today we're focused on CXL Type 3, which is for memory expansion. That's CXL 2.0 to be clear. And at a high level, CXL is an expansion of the PCIe protocol built on top of PCIe, but it's
interfaces with the CPU in a cache coherent way. In simpler terms, your CPU can access memory on a CXL device almost like it's a part of its own native RAM pool. The memory controller is certainly aware of it, with minimal translation overhead. That's unlike a block of storage or swap or anything like that, and those things operate with much higher latencies than CXL devices do. Well, how low is the latency on CXL? We're talking 200 to 400 nanoseconds, pretty typical, for random read and write, and lower than that on these smart modular devices. Compare that to the fastest Gen 5 SSDs, where the worst case latencies are around 1 millisecond for typical read and write latencies on the order of 100 microseconds. Though writes, it's pretty normal for NAND to have faster writes than reads. Another major benefit of CXL memory expansion is that it's seamless. You can add memory without unbalancing your DRAM configuration, something that we'll dig into a little bit more in this video because it's subtle and nuanced and kind of big and complicated. But here's the catch. Your server CPU and motherboard chipset and the motherboard platform must support CXL. Think of it as an overlay riding on top of PCIe lanes, but needing specialized hardware and firmware to function properly. One of the most common performance problems that I see in servers is with the physical memory configuration, and a physical memory configuration that doesn't leverage all of the memory channels that modern CPUs basically require. I mean, modern CPUs sort of want all their memory channels populated for optimal bandwidth and latency. Get that wrong and the performance can tank, even before we start talking about the new options that you've got with CXL devices. Now, memory scaling isn't as simple as just adding more DIMMs to a system. Modern CPUs like these, the Intel 6980Ps, for example, have 12 memory channels per socket. And to get the full performance, you really need to populate all those channels and populate them evenly. But here's where it gets a little tricky. Let's say that you start out with lower capacity DIMMs to save some money when you first spec the server and you get it. Later, you realize you need more memory. Upgrading often means ripping out all your existing DIMMs and replacing them with higher capacity ones across every channel. Then you've wasted some investment there, right? Or maybe you started out with every memory channel populated, or not quite every memory channel populated, and so you want to mix DIMM types. Well, that's tricky. That's usually ill-advised, and that's because there's some level of memory interleaving across channels. So if you only populate 6 of your 12 channels and then you add 6 later, the memory may not match, and then there's some interleaving going on. So if you have big DIMMs on the one side and small DIMMs on the other, that's not great either. Unequal capacities don't really interleave properly, and that leads to performance problems. And this gets into the whole nodes per socket 1, nodes per socket 4. There's all sorts of weird suffering and interesting situations you can get yourself into when we're talking about inconsistent memory latency and bandwidth from an application perspective. And memory isn't just about capacity. It's also about bandwidth and channel balance and latency, which you may not be considering when you're thinking about populating your stuff. CXL, when it enters the picture, is augmenting your DIMMs. And so CXL lets you add expansion modules, and that adds more memory without disturbing your hopefully perfectly balanced DRAM configuration. But, and this is important, CXL is also not a replacement for proper DRAM population and configuration. It's a tool for adding breathing room where your system is already optimized for its memory configuration. 8 memory channels, 12 memory channels, whatever that happens to be. You just need a little bit more capacity. I mean, okay, our system here is configured for 1.5 terabytes of memory right now. The upgrade would be to 3 terabytes. That's a huge jump in cost, for double the memory. But what if I only need another 256 gigs or 512 gigs to take the pressure off of main memory for a particular workload? 1.5 gigs of DDR5 plus 512 gigabytes of CXL could be just what the doctor ordered. I found that in AI training workloads, sure, but also database workloads and some high-performance compute workloads. Now, I've set up a demo here with MySQL to show how memory pressure impacts performance and how CXL acts kind of like a relief valve when you add more memory to the system via CXL. So here's what I did. I've artificially constrained the available system memory to just 1 terabyte, and that's a total for Linux, the operating system, MySQL, everything. And the database is large enough to use all of that memory capacity. In this setup, the performance of my test workload tanks. Queries that would normally run from memory, or at least have more caching, are now waiting on disk I/O because they're thrashing the disk because it won't fit in memory. You can see high I/O wait times, poor response times into the queries, overall system sluggishness, even though we've got plenty of CPU headroom. Now here's where CXL comes in. In this demo, I've added 4 64 gig CXL modules, giving us an extra 256 gigabytes without touching the existing DRAM. Watch what happens. With just 256 gigabytes of extra memory, now we can use that for caching, the query response times improve dramatically, and overall the system handles the load far better thanks to the rebalanced I/O contention, or the I/O contention isn't as bad because it's not the database fighting with storage. Now, this particular database was right on the edge. We didn't need to double our RAM from 1.5 terabytes to 3 terabytes, or from 1 terabyte to 2 terabytes. We just added a little bit more headroom, and we only used up a quarter of our CXL expansion capability. I've still got 12 more CXL slots. Remember, CXL memory latencies 200 to 400 nanoseconds compared to microseconds or even milliseconds for flash-based storage if I'm going to use NAND for swap or whatever. And then you got CPU overhead for block storage. Now, what I'm showing with MySQL here is, MySQL, but the same thing applies to other memory-hungry workloads, PostgreSQL, in-memory analytics, anything like that. Now, CXL memory is slower than DRAM. Let me be clear. It's slower in both bandwidth and latency. It's about double the latency. That's why I sort of limited us to 1 terabyte to start with, so I can do an apples-to-apples comparison. What's 1.25 terabytes of DDR5 versus 1 terabyte of DDR5 plus 256 gigs of CXL? Spoiler, DDR5 is faster, but the CXL configuration was only about 6.5% slower on average for these database workloads. Now, that surprised me, left me scratching my head for a little while. On paper, CXL can deliver, 32 gigabytes a second in each direction on the PCIe bus, or on the CXL bus. That's 8 lanes of Gen 5. That's about half the bandwidth of a single DDR5 channel. So, what gives us the benchmarks? Well, the performance penalty was rarely more than 10% across a bunch of different benchmarks. And the question is why? Turns out CPUs have large caches, and CXL is cached on the CPU L2 and L3, just like DRAM. Plus, Linux and schedulers and the database software are built to do a great job juggling resources and non-uniform memory access NUMA. And since my workload was built right to the edge of fitting in memory, the OS treated CXL memory just as another NUMA domain and was able to balance the load well. So the fact that modern CPUs have large caches really helped our workload. Oh, and in case you're wondering, if you look at Intel Arc, it says your server's maximum memory is 3 terabytes in the case of our 6980p CPUs. But could you add another 16 times 128 gig CXL modules on top of that for a total of 5 terabytes of memory? Yeah, you can. The CPU controller does have an upper addressable limit, but generally the number from Arc is the DDR5 native, not including CXL. I know that's a little weird, but the 6980p system can support CXL modules and go to like 5 terabytes. It's fine. Exceed 3 terabytes of memory. Let me pull on that thread for a second. Suppose this gigabyte chassis is maxed out at 3 terabytes of memory per socket, as Intel Arc specifies, but your workload still demands more memory. With CXL, you can easily add another 2 terabytes of memory per socket. Yeah, CXL is slower than DRAM, that's true, but the CPU fabric is fast enough to handle both the DRAM side of things and the CXL bandwidth combined at the same time. So the memory bandwidth here is stacking effectively. That means 5 terabytes per socket is achievable today, and with higher density CXL modules in the future, maybe even 7 terabytes. For example, one of my llama.cpp hacks used this extra capacity to load 2 copies of the AI model in RAM, one local to each CPU socket, and that avoided some cross-socket-to-socket bandwidth bottlenecks that let me scale random data scans better across multiple cores. That's pretty innovative. It's pretty interesting. It's a pretty approach. Maybe in a future video. So notice that I've also arranged my 4 CXL devices, 2 per CPU socket. You can see that in LS Topo, and you can see that in the LS PCI output, there's 2 attached to each CPU. And so memory capacity beyond the largest DIMMs available, if that's what you need for your workload, then nothing beats CXL. And like we saw with the database demo, adding CXL can often double or triple the performance for severely memory-constrained workloads. So even if the platform only supports, 3 terabytes, that's not necessarily true when you take into account CXL support and CXL memory devices. And they're so absurdly fast that there's no other option for anything faster because it's literally using all the PCIe bandwidth. In that scenario, less is more with the database. A little CXL goes a long way to solve a bad situation with database load. And if you've ever dealt with real-world databases like that, you probably already know that As you get linear growth in the database can create a geometrically increasing load on the server. That's just databases. But sometimes with CXL, more is more. And sometimes it's in the middle when we're talking about other kinds of workloads. So I tested a similar side-by-side config as the database using high-performance conjugate gradients. This is an HPC workload. It's what the Department of Energy uses for a memory-bound workload, so I thought it'd be a lot of fun to take a look at. In this scenario, my expectation was that this workload is kind of a middle-of-the-road workload, and I was sort of expecting that CPU cache thing that benefited the database workload wouldn't benefit this workload. And so if you really want to dive into the particulars of conjugate gradients, hit me up in the forum. But the bottom line is that the DDR5 configuration, the all DDR5 configuration, can manage about 125 gigaflops, whereas the configuration with 25% of the system memory composed of CXL still managed around 106 gigaflops of performance. The delta between those two configurations, in other words, was about 13%. And that's still a lot better than I was expecting for this kind of workloads. I disabled the CPU cache for the CXL devices, meaning that the CXL memory would not be cached by the host processor, and that did bring the performance way down. But overall, it was still over 50 gigaflops. And that's an impressive result, but it shows you how important the CPU platform is. And, high performance conjugate gradient workloads have gotten more optimized since the last time I looked at them, because in the past, it wouldn't have been that good. Maybe I ought to be testing some computational fluid dynamics workloads instead, because those have indirection problems as well. AI workloads? Well, we've been testing AI workloads if you've been following other videos on the channel, and the CPU matters a lot. I mean, model fine-tuning, loading large models and datasets into RAM, quantization, compressing FP32 models to int8, tabular models, memory usage balloons during training and inferencing workloads, and caching or embedding datasets in RAM avoids disk I/O bottlenecks. So it's a lot of fun. And keep in mind, this platform with DDR5 8800 support delivers about 1.5 terabytes per second of memory bandwidth, at least across both sockets. Many of these jobs are memory constrained, not compute constrained. And so you have plenty of cores, but if your model or dataset doesn't fit in memory, the performance tanks due to paging or I/O, even if you got a large complicated disk array, which is the next thing I'm going to work on. AI especially, where the model doesn't fit in DRAM entirely. For example, with a non-mixture of expert AI model where 70% is in DRAM and 30% is in CXL, I saw slowdowns of about 28%. This is our worst case scenario for the CXL testing that I've done so far. So why run these workloads on a monster server like this instead of spreading them across cloud nodes? Well, one, security, data stays local. Latency, you're only going cross-socket, not cross-rack or cross-cloud. And cost. Even though CXL is expensive and more expensive than DDR5 memory, it's less expensive than VRAM or HBM3, and that's where CXL really shines. Compared to HBM3 or GDDR7, CXL is a no-brainer for capacity expansion. And compared to DDR5, CXL isn't always cheaper per gigabytes, but you often don't need as much to solve the problem. So I don't have to go from 1.5 to 3 terabytes. I go from 1.5 to 2. And so the full DRAM capacity upgrade, you get some savings there. And remember, CXL isn't as fast as DRAM, but it's still orders of magnitude faster than the fastest SSDs that you can get. And for workloads that spill just beyond your DRAM capacity, it gives you an option other than upgrading the whole system memory. For example, in our deep sea quantization demos, adding CXL modules let us keep the entire datasets and model weights in RAM, 2 copies actually, because we were doing some other black magic. And so spending less time dealing with swap and more time actually doing quantization is great. Another example, LLM fine-tuning. If your base model is 180 gigabytes, but total memory needs are 1.3 terabytes with an optimizer state and everything else, having an extra 256, 512 gigs of CXL memory lets you run the job locally rather than splitting it across nodes. So CXL gives you flexibility. It makes sense if you have your DRAM fully populated, all your memory channels, but you need just a little bit more capacity. If upgrading the DRAM alone isn't practical, then CXL makes more sense. The big one is if your system has empty memory channels. Always populate your DRAM channels first for bandwidth and latency, and then maybe think about the CXL for a creative solution. Some motherboards support more than 1 DIMM per channel, but that also comes with a speed penalty if you have 2 DIMMs per channel, and mixing DIMM capacities in a single channel is also sort of problematic. In these systems, running 1 DIMM per channel for speed and using CXL for slower memory, which shows up on a different NUMA node, can work fantastically if you truly understand your workload. Overall, I'm thrilled to have CXL in my toolbox for these kinds of scenarios, and so I wanted to walk you through it. Do you have a workload that would benefit from CXL, or you suspect that it might, and you want to share the details that, in a way that I can understand, so I can learn something and have something to better explain and inform in videos like this? Hit me up in the forum. If you want to pick up some smart modular devices like I used in this video to experiment with and see if your enterprise workload is going to run really well, they're at Mouser. Mouser Electronics. Oh, and they didn't pay me to say all this. I just sort of like solving problems. And I've heard for a long time that CXL is coming, but it was very, very surprising that, because when they said CXL was coming, the amount of cache on server CPUs, which was much less than it is today. But now on modern server CPUs, the caching system, like the L2, L3 cache, is so good that it's really tremendously benefiting CXL modules. And that was incredibly surprising, even for like AI workloads where it's super crazy random access memory, which when it's truly like the computational fluid dynamics, when it's truly just random memory access, it's very hard to predict and cache what's going on. That's less true with like a mixture of experts thing, like I was saying, but it was still surprisingly good, shockingly good, which made me think I was doing something wrong, which is why I disabled the cache, which is what led to this video taking forever. I'm Wendell, this is level 1. Hit me up if you want to try to run something on CXL or see how CXL does. I can configure the system from 768 gigs to about 1.5 terabytes, and then we can add another 256 to 512 gigabytes of CXL modules. So let me know. It's interesting. It's very interesting, I think. All right, I'm Wendell, this is level 1. I'm signing out. You can find me in the level 1 forums and maybe comments below. All right.